so now, okay, right, so we just have to finish off. Right, so there's a lot of things you can say once you know you have a generating function. So we just have to finish off that proof. So I think a lot of it was on the homework. So, but anyway, right, so the theorem is M is closed. Right, phi. Right, so this is a Hamiltonian diffeomorphism of the cotangent bundle. Right, and then we'll say L is phi of the zero section. Right. So this is the zero section in the cotangent bundle. This is the diffeomorphism applied to it. So this is going to be Lagrangian. And in fact, it's exact. Right, because the zero section is exact, and phi is an exact symplectomorphism. Right, so it changes the symplectic form by something exact. Right. Oh, sorry, it changes the symplectic form. Changes the primitive by something exact. Right, so it maps. Right, so it's an exact. Right, so there's going to be an exact Lagrangian submanifold. Yeah, we don't really need it that much, but anyway. Right, so in other words, what it's saying is, so this has a canonical symplectic form, and it's just d lambda, right, or whatever it's going to be. So lambda is PDQ, and then what I'm saying by exact, I mean that if you take lambda and you restrict to L, well, because L is Lagrangian, this is going to be closed, right? Because if you differentiate this, you'll get omega restrict to L, which is 0. Right, but what I'm saying is this is actually exact. Anyway, I won't really use that too much. But, but in particular, it's the image of a Hamiltonian diffeomorphism. Right? Hamiltonian diffeomorphisms are symplectic, so they're going to map Lagrangian to Lagrangian, and this is the Lagrangian that we're interested in. All right, so that's an exact Lagrangian submanifold, right? And then the theorem is, so the claim is that L has a generating function. S, right, so it's a map from M times some Euclidean space, right, for some L. Which might be large, right? But anyway, it's a natural number. But anyways, conceivably, this is a big number, the way the proof goes. Right, so the proof was always you start with the zero section, you move it a little bit, you have to add on a factor, then you move it a little bit more, then you add on another factor, and so this thing can be very large. Right, so then L has a generating function, so what does that mean? So in other words, L is the set of partial ds dx, which you think of as an element of the cotangent bundle at xm. So this is just the partial derivatives in the x direction, or in other words, the derivative evaluated. Right. This is just right. So this is ds by definition. Remember, this is ds restrict to txm, which is a map from txm to r. So in principle, ds is a map from the tangent bundle of this whole thing. You just restrict to the first factors. So this is it. So L is ds dx, and you evaluate at all points. All right, so it's ds dx at x psi, such that ds d psi at x psi is 0. Right, so that's what we're claiming. Right, so we're claiming that if you take an exact, if you apply a Hamiltonian diffeomorphism to the zero section, you're going to get a new Lagrangian, and the theorem says it's of this form. And it has a particular generating function. Okay, right, so we know a lot of this already. Right, so just basically it's what we already know. Right, so the proof is, right, so what we know, right, so we know, well, the first thing is if, we'll say if psi is a Hamiltonian diffeomorphism of the cotangent bundle of Rn, well, maybe say compact support, right? So you don't want it to mess around at infinity. So anyway, right, so this is a non-compact manifold here, but anyway, if you take a compactly supported Hamiltonian diffeomorphism of that, then psi of the zero section which is a copy of Rn, has a generating function. By the way, so this has a generating function. Moreover, it's quadratic at infinity. Right, so it's moreover. That's right here. Right, so moreover. S is a quadratic at infinity generating function, right? Which means that S of x psi is just some positive definite quadratic function of psi when the absolute value of psi is bigger than some constant. Right, so imagine, right, so the domain of this thing is a compact manifold times Euclidean space. If you go out far enough in the Euclidean space direction, this function is just a quadratic of the Euclidean factors. So it's kind of right. So we'll see in a second. This is kind of important. Right? So you don't want any odd function. Right? This kind of function means you get a bit more control. Anyway, right. So in this case, right, what do we know? Right. So if you take a compactly supported diffeomorphism of that, then the image of the zero has a generating function. Well, right. It wasn't quite quadratic at infinity, right? But we could say that such that. So it's kind of compact on a closed set, right? Quadratic at infinity on a closed set. Right, so let's say, right, so if you're given a Hamiltonian diffeomorphism and a constant bigger than 1, right, or just a constant, then this has a generating function such that, has a generating function S1, right, so such that S1 of x psi is some quadratic function of psi for all okay, right. So if the absolute value of x is less than c and psi is bigger than some other constant. So it's right, which is already really clear. So at least right, the way the proof went, this s is quadratic in x as well when x gets very large. So it doesn't quite satisfy this. Right? So the problem is in this case, if you take x very large, you can't find a uniform constant on the psi. Right? But at least if you restrict x to a compact set, then it's quadratic at infinity. Right, so in other words, right, so you could rewrite this. So you could say that, right, so S1 restrict to, if you look at this, the restriction to the set of x less than c, this is, well, this is quadratic at infinity. It's a generating function of the element. Right, so that's all we really care about here. So at least it has this property out in a compact set. So, okay, so that's one thing we proved. Right, and this was this kind of induction argument. Right, you start with the zero section that has generating function just q of psi. Right, so you start with the zero section, and then you start kind of deforming it bit by bit. And if you deform it by a very C1 small amount, then you have that composition formula for how the generating function can change. Right. So the outline, so you start with the zero section, you're okay there. Then you deform it by a tiny amount, and you're still okay because if you deform it by a tiny amount, it's given by a Lagrangian correspondence. And if you have a Lagrangian correspondence of a certain form, then the image is still going to have a generating function. So you deform it by a certain amount, and then you keep going by very small amounts. All right, so that's the first thing. Right, that's number one. Right. Then the second, okay, so we don't care about Rn, we want a closed manifold. Right, so the second thing is if, right, so now, right, so then there's a whole bunch of stuff. So suppose M contain, right. Got this chalk and I'm messing it up. Right. Suppose that M we contain in Rn be closed submanifold. Right. Then there's a bunch of facts about that. Right. Okay. So then, right. So then 2 part 1. Right. I put some of this on the homework. We're going to talk about this. Right. So 2 part 1 is that if you take right, if you take the cotangent bundle restrict to M, right, so I think we call this T star M Rn, right, So this is the set of well, x comma p in the cotangent bundle of Rn, such that the base point is in M. Right, so that's it. So just the whole vector bundle restrict to M. So 2 part 1 says that this is co-isotropic. So it's co-isotropic, and the leaves are just subspaces of, right, with leaves. Well, affine subspaces of, right, of the fibers. So in other words, right, so what was this? All right, so if you write this as k, right, so if you write k omega x, what is this? This is the kernel, well, right, so what does this mean? So this is the tangent space at x of k omega complement, right? And I claim we know what that is, right? So this is exactly, so it's going to be vectors in here, right? So what is that? Right, so it's a vector in here which is tangent to a fiber, right? So okay, so we have to think, right? So what is this? So it's going to be right? Okay, right. So this is going to be contained in. Right. So that's right. It's given by. Right. It's really right. So I have to be a bit careful here. Right. So where? Right. So if you, right. So now I'm looking at the tangent space of this whole thing. First of all, I claim this has like a fiber subspace. Right. So you can talk about the tangent space. Sorry, I shouldn't write x here. Right. So it's x comma p. Right. X comma p is supposed to be a point in K. Right. So you take a point in K. We want this canonical subspace. Right. So what is this? Right, so if you look at the tangent space to xp of omega k, that contains the tangent space xp of just the fiber direction, right? Right. So this is right. Okay. Right. Well, right, so if you look, actually, right, if you look along anywhere, if you look along Rn or you look along N, this cotangent bundle is a product, right? The cotangent bundle, so this is exactly M times Rn. Right? So all I'm looking at, right, so here I just mean the tangent space to the first factor, that's contained in here. Right, but this is a tangent space to Rn. So you can identify this with Rn itself. Okay, right, so what's this thing? This is given by k x omega xp. Right. So I want to choose vectors in the, sorry, it should be cotangent bundle here as well. Right? Right. So what is it? It's the set of, right, so it's exactly, right. So you want to move in a direction where if you project down to the base, it vanishes on M. Right, so what does that mean? Right, so it's some kind of identification here, right? So it's the set of P prime, right? So P prime has to be in the cotangent bundle at xp of the Rn direction, all right, such that. So this makes sense. Right, so I'm thinking of it as a cotangent bundle to the, right, so it's a vector, right. Sorry. Can never get this right. Right. So what is this? Sorry, it's in the. Let's put another T here. That's right. Right. So where this. Right. This is the cotangent fiber. Right. All right. Right. Right, so the picture. Right. So all you just have m times Rn, right? So it's Rn times m, you have m. Then it's a product, it's like a fiber bundle, and the fibers are Rn, right? Which are just the cotangent fibers, and I want to choose P prime tangent to the fibers. Right, so that's what I'm trying to say, right? Right, so P prime is tangent to the fiber, right? But the tangent space to the fiber is exactly the same thing as the fiber, right? Because this fiber is a vector space. So if you're tangent to a vector space, you're like an element of the vector space. And the vector space is the cotangent bundle of Rn, so you can evaluate on vectors in Rn. And so it makes sense to say P prime. You can evaluate on the, right, so what is this? So, actually, wait a second. Right, so this is, write this down. I've got the xp in the wrong place. Right, so it's the tangent, right, it's the tangent space at xp to the cotangent space at x. Right, that's what I want. Right, so x is a point on M. Right, now what I'm talking about now. Right, so x is a point on M. This line here represents the cotangent bundle at x of Rn. Right, that's supposed to be the vertical line. Then I want to choose a tangent vector to that. Right, so this, right, okay, so wherever it's going to be. Right, so there'll be a little tangent space here. This is the tangent, so this will be P. This is the tangent space at xp to the fiber, right, to T star x Rn, which is a subspace of the tangent space of xp of k, which is a subspace of the tangent space xp of T star Rn. Right. So it's a big mess, but anyway, but that's what you have here. Right? So P prime is going to be, so it's tangent to this whole space, but in particular it's going to be it's actually moving, it's pointing in the fiber direction. Right? So it's in this particular, right, so it's a tangent vector to the fiber, which is, the fiber is contained in K, so it's also a tangent vector to K. Right, so this makes sense. Right, so P prime is a tangent vector, right, so it's a tangent vector to the fiber. Tangent vectors to the fibers, right, so this, right, so what do I mean here? Right, let's write this again. That's what I mean here. Right. So what do I mean? Right. So the right. So what have we got here? Right. So the tangent space at xp of the fiber T star x Rn. Right. So this is a tangent space to, well, right. It's a tangent space to a vector space. So this is canonically isomorphic to, right. To just the fiber itself, right? Because the fiber is a vector space. Right, so you're okay with that, right? So if you take a tangent space to a vector space, it's the same thing as the vector space. Right? So P prime is in the tangent space of the fiber. That's the same as the fiber itself. And if you take an element of here, you can evaluate it on vectors tangent to the base. Right? And what I'm saying is, if you restrict to M, you get 0. So that's it. So that was the. So that was exactly the. That's the coisotropic distribution. Is that? Okay. Right. Okay, and then we checked last time. That has all the right dimensions. That's exactly what it is. And if you quotient out by these directions, what you're going to be left with, you're going to be left with cotangent vectors that evaluate non-trivially on M, but that's exactly the cotangent bundle to M. So that's right. So kind of carrying on with that. Right. So, okay, so that's the coisotropic subspace, and if you take the this thing here, T star M Rn, and you do the symplectic reduction with that K, that is isomorphic just to the cotangent bundle. Okay. Right. Okay. Right. So we can talk about this later, but so I've stuck this on the homework. So that's so it's kind of clear what the map is here, right? Right. So the map is right. Okay. So you take something in here. What's a point in here? It's a point x comma p, and you just map it to. Well, there's only one thing you can do. Right. So I want something in the cotangent bundle to M, right? And it's going to be right. So it's going to be something in the cotangent bundle at x of M, what is that? Right, so we have the x, the base point here. I want something in the cotangent bundle of x to m. What does that mean? I want something which acts on cotangent or something which acts on tangent vectors to m. P acts on tangent vectors to Rn, so you can just restrict it. So this is just P restrict to T x m. And the claim is that this is an isomorphism. So it's basically, I mean, you can sort of tell it's one-to-one because what does it mean? What is this quotient map by K? I'm just identifying things which differ by so which differ by moving in this direction. But if you move in this direction, you're not going to change how you evaluate on M. Right, so this has to be an isomorphism, and then the claim is this is symplectic. So that's the symplectic reduction. All right, so we're going to talk quite a bit about that. Right, so that's the first thing. Right, so if you take a closed submanifold of Rn, you get this co-isotropic thing, and then the symplectic reduction is exactly the cotangent bundle to M. Right. So okay, so you get that. Then, right. So then the next thing is part 2. So it's 2 parts. Right. The next thing is if you take. Right, so when you have a symplectic reduction, it takes Lagrangians in the total space to Lagrangians in the reduced space. Right? So next thing is if L is contained in the cotangent bundle to Rn, right, that's the total space, then you can do the symplectic reduction. Right, so if L, suppose that has generating function, call it S. So now this is going to be a map from Rn times Rk to R. Then you can do the symplectic reduction. Then the symplectic reduction. The L tilde or L subscript K. Right. So what is it? So this is now contained in the cotangent bundle to M. So remember how you could do here, right? So this is right. So we have a map pi from K to T star Rn K, which is just symplectomorphic to T star M. Right. So you have this map pi, and then what's LK? Right. So and and LK, you just take L intersection K and then apply pi to it. So that's the symplectic reduction. And the claim is that this also has a generating function. So if the original thing has a generating function, you intersect with the co-isotropic, push it down to T star M, that also has a generating function. And the symplectic reduction, this also has a generating function. S, and then the formula is just something like S of, so it's the same, right, but now S is a map from M times Rk to R, and it's just exactly the same formula, right? So S of x psi is S1. Psi. Just the restriction. So it's fine, good. All right, so now, right, so that's the first, right. So we're interested in closed submanifolds. The cotangent bundle of a closed submanifold is a symplectic reduction of the cotangent bundle of Rn. Right, so Lagrangians in the cotangent bundle of Rn give you Lagrangians in the cotangent bundle of M. And moreover, if this thing has a generating function, then this thing has a generating function as well. And also, if, right, sorry, maybe let's call this S tilde. Well, I think I'm saying everything in the quotient is with a tilde and everything at the height is without. Do it the other way around. Right. So what do we know then? Right. So I know that if things up here I have a criterion for getting things in Rn to have a generating function. If the thing for Rn has a generating function, then when you push it down to the quotient, you still have a generating function. Right. So now we can basically prove the theorem, right? So it's more or less it. Right? So now, Right. Right, so I want to get a generating function for Lagrangians in the cotangent bundle of R, cotangent bundle of M. To prove that, it's enough to show that it's the reduction of something with a generating function in T star Rn. Right? But everything in T star Rn, which is Hamiltonian diffeomorphic to the zero section, has a generating function. Right? So it's right. So the last point is right. So the last step. Right, is right. So you suppose L tilde in T star M is Hamiltonian isotopic to the zero section, is L tilde. So it's going to be phi of the zero section with some phi in ham T star M. Right. So this is exactly the kind of thing we're interested in. I want to show then, right, so then the claim is that L tilde is the symplectic reduction of some L, right, so for some, right, so L is now going to be in the cotangent bundle of Rn, and I want this thing to have a generating function, right? So if I knew that L had a generating function, then by this statement, the symplectic reduction would also have a generating function, then I'd be done. And more, by the way, if S is quadratic at infinity, then this is going to be quadratic at infinity as well. So you're fine with that. Right, so it's, right, so this is what we need to prove. Right, so the claim is if something in the cotangent bundle of L, of M, is the symplectic reduction of something in the cotangent bundle of Rn, I need this to have I want this thing to have a generating function, but to know that this thing has a generating function, it's enough to know that this is Hamiltonian isotopic to the zero section. Right. So for some L with L equals psi of the zero section in Rn. Right. So with right. So psi is now Hamiltonian, maybe with compact support on T star Rn. So this proves everything. Right? So putting everything together, this proves the whole thing. Right. Right. So I know. Right. Right. So this does this because I know that L has a generating function. Right. So this proves the theorem. Right. So this proves the theorem. Right. So Y. Right. So L has, well, sort of quadratic at infinity. Put that in inverted commas. Anyway, good enough. And L has a generating function. Maybe just worry about generating function first. I claim this is pretty easy to fix. Right, so L has a generating function by step 1. Right? Right, because L is the image of a Hamiltonian. But this implies that L tilde, which is the symplectic reduction of L, this also has a generating function by step 2. There's a quadratic at infinity generating function by step 2. Right? So then I'd be done. So there's all right. So all you need to show is if you start with something which is Hamiltonian isotopic to the zero section in the cotangent bundle of M, it's the symplectic reduction of something which is Hamiltonian isotopic to the zero section in T star Rn. Okay, so we just have to, so the claim is all that's left, that's it. And this proves everything. But to prove the claim, I can even tell you exactly what L is. So to prove the claim, so we can even be more specific. Right, so for proof of the claim, well, phi is Hamiltonian. Since it's Hamiltonian, it corresponds to a family of functions. Right, so phi is generated, it's Hamiltonian, so it's generated by a function, or a time-dependent function, h, from m times r. So remember, this second r is just there for confusion. You can think of it as a function if you like, but anyway, so the map is x comma t. Just often you write it like this, just just to kind of emphasize that t is just, kind of an extra parameter, really. Right, so phi is generated by that, right? So it's going to, because it's Hamiltonian, it's generated by some function, right? So in other words, phi is the floor of the time-dependent vector field xh, or xht, right? And then to define xht, the formula is xht contract with omega, right? So this is the standard, right? So this is the standard form, on t star m. This has to be dht. So just think, for each time, so the idea is in this formula you're fixing time. Right, so for each time you differentiate h, you get a one form, and then, right, so this just means omega of xht, comma blank. Right. So you differentiate h, you get a one form, and then I claim every one form is of the form x omega of x comma blank. And that's because omega is non-degenerate. Right? So omega gives you an isomorphism between one forms and vector fields by this formula. Right? So every vector field corresponds to a one form by this formula, and then the theorem is that's an injection because omega is non-degenerate, or it's onto because omega is non-degenerate. All right, so okay. Right, so that's the assumption. Right, so phi is generated by a function, some function. Right, we're looking for an L. Right, so this gives you L tilde. Right, I'm looking for an L, so we can be more specific about the claim. Right, so I want to get a function on t star Rn. Right, so let G, right, this has to be a t star Rn. Well, maybe this is time dependent as well. So actually almost anything works. Well, some hypothesis, right? So be any function such that, right, so the assumption is, right, so what do I want to say here? Right, so G, right, so G of xp. Right, so if you want to evaluate at a point, all you do, you just, maybe there's a t. Right, so xp is going to be in here. Maybe there's a time. Right? So g of xp t, right, so what do I want to do? So xp is in t star Rn. I just want to do the isomorphism to push it down to t star. Right. Anyway, this is h of pi xp. Right, for all xp and k is t star m Rn. So that's it. So g is just the lift of a function. So I'm only defining it on k. I don't care what you do anywhere else, as long as on k it has this formula. Right. So in other words, right. So what is pi? Right. So where? Right. So pi is the map from t star m. T star Rn. Actually, right. Sorry. Right, so t star m Rn to. So that's the quotient. Right. So that's right. So this. Right. So this is a symplectic reduction map. So what does this do? So this is a submersion from here to here, and the kernel is exactly the distribution. The distribution corresponding to k. Right. So it has kernel of pi. Right. So let's say the kernel at xp of pi is equal to k omega at xp. So that's the symplectic reduction map. So in other words, right, so you could rewrite this. So in other words, you could say that G equals pi star H on K. right? Right, so h is a function here, right? This is k. Right, so if you take a function here, you have a map from one to the other, you can pull back functions. Right, that's how it goes. Right, you have a function on the domain, you can pull back to get a function on the range by this formula. Right, so this is just h composed with pi. Right? And that's what I want it to be on. Right? That's what I want it to be on k, and then just extend it however you like. I don't care. Right? So that's it. So I claim, right, so then you can be more precise about this claim. So then the claim is we can let L is just the image of, is the floor of this G. So more precisely. All right, so more precisely. Right, so more precise. Right, so you can take L equals, well, the floor. Right, so the time one, or whatever it is. Right, so the time one flow of x gt. So that claims this works. Well, certainly it's the image of a Hamiltonian diffeomorphism. Well, I mean, you might say, well, okay, it might not have compact support, but I don't really care what you do outside of a compact set. It's not going to affect anything. So you can cut it off however you want. So it's certainly the image of a Hamiltonian diffeomorphism. All you've got to check is that if you take this and do the symplectic reduction, you get back to the start. So that's it. So claim this does the job. In other words, if you take that L and do the symplectic reduction, then you get the L tilde. Well, right. So then you get L tilde, which is phi of the zero section in M. So that's it. So that's all we have to do. Right? So it's a concrete thing to prove, and once that does everything. Right? Because exactly the same reason, right? Because L has a generating function, right? Therefore, the symplectic reduction has a generating function, but that symplectic reduction is exactly came from kind of an arbitrary Hamiltonian diffeomorphism. So that's exactly what you have to prove, right? So, right. It's supposed to be a submanifold, right? It's the time one flow of xt applied to the zero section in Rn. Right? So you lift the function, right? So you have a function on the cotangent bundle of M. You lift it to get a function on K. Extend however you like, I don't care. Right? So G, right, so maybe another like, so extend, I don't care. Extend anyhow, in any way. So in principle, this only defines a function on K. But you can extend it to the rest of Euclidean space however you want. So that's it. Right? So then I'm claiming, so this then gives me a function on T star Rn. I'm claiming if you take the Hamiltonian flow of that, which is always going to have a generating function, then the symplectic reduction of that is the submanifold you want. And therefore, the submanifold you want has a generating function. Right. It's logically correct. You guys are younger than me, so sometimes my logic's slightly shady. I think, right, okay. So that's all we have to prove. So we just have to prove that. So this is sort of step 3. So this is a few things. Right, so step 3, part 1. Right, okay, so what do we have to check? So the first claim is, okay, we're flowing around by this vector field. The first claim is that this vector field preserves K. All right, so step 1, x gt is tangent to K. Right, which implies that the flow, the flow, if you start differentiating, the flow of x gt maps K to K. So if a vector field is tangent to a submanifold, and you say x dot is equal to x gt, x is going to, if you start in K, you're going to stay in K. Right? So direction of flow maps K to itself. Right? So in other words, right, what I mean is, x gt of xp is in the tangent space of xp of K, right, for all xp in K. Right, so in principle, this is a tangent space to the whole of the cotangent bundle of Rn. I'm saying this vector field is actually tangent to the coisotropic. Right, so it maps the coisotropic to itself. Okay? Right, so why? Okay, I'll put this on the homework just to check. But right, so why is that? Right, so well, okay. Right, so this is the thing. Right, so the idea of that. One. Well, okay. Right, so the thing is, right, so the map, I'm going to call it I. You can take the, right, you can take the complement, maybe you did this already, right? You can take the complement of the coisotropic. Oh, right, so right, so let's say right, okay, so let L be some submanifold. So L is contained in the tangent space at xp of the cotangent bundle of Rn, and L plus, right, L plus the tangent space of xp of K is tangent space xp. Okay, right, so we have, right, so you have all of T star Rn. You have the coisotropic submanifold. I just want to say that L is a perpendicular subspace. Right? So something. So in other words, it doesn't intersect with K, but it adds up to the whole thing. So you take some L like that, any old L. Right? Then I claim that there's a map from this space, right? So from the coisotropic subspaces, the coisotropic distribution to L star. Right? So what's the map here? You just take a, well, right, so remember this is a subspace of the tangent space xp of K. So there's a map from this subspace to L star, right, it's just a natural map, right? So they're both vectors. So you just map a vector to omega v comma blank. And I claim this is an isomorphism. Right. So well, so we can check dimensions. Well, if you want to prove something's an isomorphism, it's, first thing to do is just check the dimensions are the same, just in case. Right. So dimension of K. That's dimension of T. Well, it's good to sort of warm up anyway. Right. Right, so dimension of K is, this is all cotangent vectors to M. So you have, right, so let's say M, right, dimension of M is M. Okay, so if you're in this is all cotangent vectors to M. So you have M dimensions on the base, and then N in the fiber. In fact, this is exactly a product, right? So this thing is just M times Rn. So dimension of this is M times Rn. Right, so that's that. The dimension of the subspaces, right, at xp. Right, so as a general formula for that, the dimension of the symplectic complement is the dimension of the ambient space minus the dimension of K. So this is the dimension of T star Rn minus dimension of K. T star Rn, that's 2n minus dimension of K minus M plus N. This is N minus M. Which is positive, by the way. Right. Just as well, right? Because M is a submanifold of Rn. So dimension of M has to be less than Rn. All right, so that's dimension of, okay, that's dimension of this. Right, but then what's the dimension of L? Right, so, right, so meanwhile the dimension of L, well, it's obvious, of course it's the same thing, right? In fact, basically by definition, I mean, it didn't even need this out. By definition, right? So dimension. So because this plus this is equal to this, the dimension of L has to be the dimension of this minus the dimension of this. But I've just used that to define how the anyway, okay, that's right. So dimensions check. Actually, we wouldn't have even needed numbers here. I've basically used this, right? I've used this formula as the definition of dimension of that, which straight away. Okay, anyway. Very good. All right. Okay, so at least the dimensions are the same, right? So what else do you have to check? So you just have to check it's either injective or surjective. If we show that it's injective, right, also I is injective. Yeah, right, injective. Right, so if not, right, so by contradiction, there exists a V in K omega such that omega V W is 0 for all W in L. So if it's not injective, that's true. But what do we know? But K omega is the kernel of omega restrict to K. Right? But we know that omega of VU is 0 for all U in K. Right? Exactly, because V is in K perp. Well, I mean, take tangent K, right? So it would be tangent XP. Right? Okay, but this implies, but this implies, right? All right. So now just take any vector, right? So any. Have to be R, right? Right, so any R in the tangent space of the whole space, right? So any R tangent to this thing can be written as R equals V plus U for V in W plus U. W plus U for W in L and U in T XP K. From this formula. Right, so you take any vector to the tangent space, you can have it as an L component and a K component uniquely, but this implies that omega V comma R equals 0. Because omega of VW is 0 and omega of VU is 0. And that's a contradiction. Since omega is non-degenerate. Right, every vector has to pair with something. Right, so anyway. Right, so I'm trying to, okay. So you have all that. All right, so I'm trying to claim this, right? XGT is tangent to K. Right, you agree with that? So XGT is tangent to K. Right, okay. Right, so I'm trying to prove this. Right, so proof of 1. Again, right, so proof of 1. If XGT is not in the tangent space to K, then, right, it's not in the tangent space to K, it has to be in some other subspace, then you could extend it to a complementary subspace. Right, so then XGT is in L for some L with right, L plus right, so either, right, so you have the subspace of K, right, you have the tangent space to K. So I'm trying to prove that this thing's tangent to K. If it's not in K, it's somewhere else. And if it's somewhere else, you can just add in other vectors which are complementary to K, and then get a subspace. All right, so either it's in tangent space to K or it's not. If it's not, you could extend it to a to some subspace. This is supposed to lead to a contradiction here, so it's not that. right, so what does this mean? So this implies, right, this, right, okay, so xgt is in L, so that means there's going to be a vector, right, there's an element of the dual space to L which evaluates non-trivial on xgt. So this means there exists a V in k omega of xp such that I of V acting on xgt is not equal to 0 by this from above, since I is an isomorphism. So I of V you can assume to be anything in L star, right? But something in L star is going to evaluate non-trivially on this. Okay, but what is I of V of xgt? This is omega of V comma xgt. All right. But xgt is a Hamiltonian vector field. All right, so this is a formula here, maybe a sign. So this is exactly d gt evaluated on V. All right, but now now I can just compute this on, so since V is tangent to K, I can just compute this on K, right? So just write out V is tangent to K, so I'm just going to restrict G to K and evaluate there. So this is exactly, and when you restrict to K, G is equal to H composed with pi. So this is dHt composed with pi of V, which is dH composed with d pi of V. Right, but what's pi mean here? Right, pi is projection along k omega. So this is 0. Right? That's exactly what pi is. Right? So pi is projecting on the kernel of exactly what I mean. Right? So since the kernel of pi. So another way, so if you think what you're doing here, right? So you just kind of you have your base, right, or base times r, and then we kind of have k, right? So this is sort of all the same picture, right? So k is fiber over m, and the tangents to the fibers, these are the k omegas, right? So that's kind of the picture here, right? Right. So you look at all of k, which looks like m. It's a product. It looks like m times Rn, but then inside here you have these subspaces which are the coisotropic distribution, and they're exactly the kernel of the projection. So if you have a function on m and you just lift it to the whole thing, it's going to vanish on these directions. So in fact, right, so g is constant in these directions. It's exactly how I'm defining it. Right, so I'm just defining g by take a point, project it to the base, and evaluate h there. Probably erased it. Anyway, right, so G is H composed with pi is constant on these fibers. Right? Exactly because it's fibers of pi. Exactly because it's defined by projection. Right? So if you take 2 points on the same fiber, pi of them is going to be the same, so the value of H is the same. So G is constant on the fibers, which is the same thing as saying that dG vanishes on the fibers. So this has to be 0. All right. Okay. So that's all right. That's right. So G preserves K. Right, so G is correct. All right. So G preserves K. So what we're saying here, right? So psi is the flow of g t. Oh, sorry, xgt. Right. Right. So I know that psi of k equals k. So that implies that right, okay. Right, so the 0 section in Rn intersection K, well, or maybe up to isomorphism. Right, so what is this? This is just, right, so the 0 section in Rn is just all 0 cotangent vectors. If I intersect that with K, I just get 0 tangent vectors over M. So this is just M. Right? So it's the set of x comma 0. So 0 is in the cotangent bundle at x. Right? So that's the 0 section intersection K. Right? So this implies, so now let's apply psi to this formula. Right? So this implies that, well, right, so psi of the 0 section in Rn intersection psi of K is equal to psi of M, well, or equivalently, but this is just equal to K, because psi of K equals K. So, right, so if you look at, right, so if you look at the flow of this xgt, right, I'm interested exactly in where this intersects K, right, because I want to do symplectic reduction on this. Right? So this is going to be eventually, this is going to be our L. Right? So L, well, maybe if it's the time 1 flow. Right? So L is the time 1 flow of this applied to the 0 section. So if you want to know where L intersects K, it's exactly this flow applied to M, or applied to the 0 section in K. Right? Because K goes to itself. So, right. So as you move things around, nothing is going to come into K and nothing's going to go out of K. So if you want to know where this intersects K, you just need to work purely in K. Right? So in principle, this symplectic reduction could be complicated. There could be a point from way out in Rn, which somehow moves around and comes back into K, but that doesn't happen. K is mapped to itself. So the only stuff that's going to intersect K is the stuff that started in K already. So, okay, right, so recall, right, so what we're trying to do here, so recall, right, we're interested, I'm interested in L, which is psi of the 0 section, so this is the flow of G, psi of the 0 section in Rn, intersect K, and then I want to do the projection to that. Well, question mark, right? Right, so I'm trying to compute this. Right? Right, so I want to take my Lagrangian in the total space, intersect with K, and then project down on the cotangent space to M. So hopefully it's going to equal just to L tilde. Okay, so what is in, right, so, so what are these points? Right, but what is this? But this is just, well, right. Right, so psi of this intersect K. So this is exactly psi of the 0 section. So I just need to know what happens to the 0 section in M as you flow under G. So that's right. So in other words, so just rewriting this again. So if X, or I'll say Y, right? So if Y is in that space, right? So if Y is in L intersection K, then Y equals psi, which is the, right, remember that's the time 1 flow of xgt, of x for some x in M. Right, where I'm thinking of M as being M times 0 in the cotangent bundle of Rn. Right? So that's the only possible thing it could be. Right? So nothing's coming in from outside. The only stuff that's in K after time 1 is the stuff that started in K at time 0. And the only stuff that started in K was the 0 section in M. So that's all it is. Right, so what happens to X? Right, so let's just work out. Right, so how does X move? Right, so it's right, so over time. Right, sorry, so if psi t is the time t flow, what do I know? Right, so I know that d by dt of psi t of x, so it's the flow of this vector field, xgt. So this is xgt at the point psi t of x. All right, so that's it. So that's how it evolves. Right, so if you know where it is at time x, then there's the ODE. Right, if you know where it is at time x, and you want to know how it moves exactly according to gt. Okay, so what? Right, so I'm interested, okay, so that's how that point moves. I'm interested in what happens as you project it. Right? So what does this mean? So if we apply pi, right, so these are both vectors. So if we apply pi to this, so this implies that d pi, with psi t of x, I guess, of d by dt of psi t of x equals d pi of x gt psi t of x. All right? So you can project everything down to the base. Anyway, so the second claim is that this is exactly the Hamiltonian vector field of H. Okay, by the way, right, so this thing here, right, by the chain rule, this is d pi composed with dt. This is just d by dt of pi composed with psi t. Right, that's all that is. Right, so if you, right, so d by dt just means differentiate and evaluate on d dt. If you differentiate this, you're just going to get d pi composed with d dt of psi t. Right, so what I'm measuring here when I go d pi composed with d dt of psi t, that's just the derivative of what you get in the reduction. So claim 2. So claim 2 is that if you go d pi of the Hamiltonian vector field of gt at some point, this is, we should say y, this is exactly x ht at pi of y. And that would do it. Right? So that would mean if you start with a point on the 0 section, it's going to start moving around in k, then you could start applying pi and start moving that around. Right? So in other words, so this implies that pi of psi t of x moves tangent. Right? So when you project it down, it's moving tangent to d pi of xgt, but I'm claiming that d pi of xgt is x ht, right? Which implies that at time 1, pi of psi 1 of x is going to equal phi of x. Right? So this is the time 1 flow of ht. Make sense? Right? So k is mapping to itself. Right? So if I want to know where something, I don't know where anything ends up within k. All I care about is what happens when you project it down. But as you project it down, that's going to give you a path in M, and that path is going to be tangent to this vector field. No, that's correct, right. Sorry, right, so x, right, remember, it's let's say project to M. We put project to the cotangent bundle of M. Right, so once you have this formula, that proves everything I claim. Make sense? Right, so we're looking, right, so in principle, right, so I shouldn't be drawing M on the bottom here. We're really projecting down onto the cotangent bundle of M. So this is the pi. So I think I just wrote M here. Right, so remember, symplectic reduction takes k to the cotangent bundle of M. Right, not M itself, of course. Anyway, right, so you start with x here. Right, it moves around in k. Right, so that's what's happening here. Right, so this is right, so this is the psi t of x, but then you project down to the base, you're going to get a path in the base. Okay, right, but if this thing is moving tangent to x gt, then when you project down to the base, you're going to be tangent to x ht. So the projection is actually moving according to the Hamiltonian vector field of h. Right? So there could be some vertical components, but we don't care. It's not going to affect things at the end of the day. You get the picture here? Right, so it's basically moving in x according to xht, maybe some vertical components, but they're not going to affect the reduction. All right, so that's it. So you just need to prove this formula. And then we're done, I think. That's good. Okay. Right, so that's it. So we just have to prove this, right? But what do we have to do? Right, so we need to prove 2. Right, so you have to prove that. Right, so proof of 2. Right, so what am I claiming? So I'm claiming that, right. Okay, right, so I'm claiming that d pi of xgt is equal to xht. Right. Well, I'm dropping the point here, it doesn't make any difference. Right, so I'm claiming when you project the Hamiltonian vector field of gt, you get xht. Right, what does that mean? So that means, it means that this is the Hamiltonian vector field of ht. It means if you work out omega tilde, right, so this is the reduced symplectic form, right, so this is the reduced symplectic form, which, as we proved, that's just the symplectic form on T star m. If you evaluate that on d pi of xgt, comma blank, this should equal dht. Right? That's exactly what it means. Right, so this is the defining equation for the Hamiltonian vector field. So you take the symplectic form on T star m, you evaluate this blank, this should be dht. That's what we have to prove. Right. Okay, so that's true if and only if. Right, so I have to check this for all vectors. But every vector, since this pi is a submersion, I can check, I only need check for vectors of the form dw. Right, so this is true if and only if omega tilde of d pi of xgt, comma d pi of w equals dht of d pi of w. So I'm just substituting d pi of w into that. But it's enough to check for vectors of that form. So it's if and only if this, for all w in the tangent space of K, since pi is a submersion. Right, so pi is just a quotient map, so pi is a submersion. So you have to just check this formula. Right. But what is this? But this is if and only if. Right, so now remember the definition of omega tilde. Right? So by definition of omega tilde. Right, so what is the symplectic form on the reduction? If you take the symplectic form on the reduction, if you want to evaluate it on the projection of two vectors, you can just take any lift of those vectors and evaluate up a height. So by the definition of omega tilde of d pi of u, d pi of v, you just evaluate up a height on xgtw. W, right? But now dht composed with d pi, this is dht composed with pi of w. But then by definition of gt, this is just ht composed with pi is just gt. Right? So this is just dgt. That's all we have to say. Right? And this formula is true. This is true because xgt is the Hamiltonian vector field of gt. All right. Okay, so that's it. So So that's our big labour done then, Helen, right? So now we've got this. Right, so a lot of this is kind of, I've sort of put it on the homework as well. But, all right, so now that's it. So now everything has a generating function. So now it's supposed to cache in, and now you can just like write some theorems down based on that. So now you can sort of somehow describe Lagrangians, you can describe symplectomorphisms, you can do whatever you want with that. All right, so what's maybe now is, we could take a little break now, and then we'll cache in. Right, so now you have a nice description of Lagrangians, and now presumably you can start, proving theorems about them because you have a big tool. So given a Lagrangian, take the generating function, and then say something about the generating function, apply something about the Lagrangian. All right, so maybe we'll take a little break, then we'll prove some little theorems about that. Well, I mean big theorems, right? So big conjectures you can prove now just based on that. All right, okay, so I'll have a little drink, and then I'm back in a second.